In this video, we're going to look at many of the different ways we can use exponential and logarithmic techniques to solve equations that involve either exponential or logarithmic components. Let's start with the simplest examples, some exponential functions where both sides of the equation involve the same base. Now, it might not seem that way in the beginning. They'll oftentimes try and hide it from you, but with a little manipulation you can turn 25 to the x equals 125 into a power of 5 on both sides of the equation. And once you have this situation where the bases are the same, you know the powers must be the same, so now you're just solving for the powers. Same thing over here, you rewrite 9 to the x as 3 squared to the x, which becomes 3 to the 2x, and now you're solving for powers. So that's the simplest example of exponential problems. They're not always going to be this easy. You can't always make the bases the same. And once that happens, you have to start using some techniques of logs. So an example like this. If we're given 2 to the x minus 3 equals 17. Now this up here is a bad typo, right? It's actually supposed to be 5 times 2 to the x minus 3 equals 17. And then you can see the first step is to isolate that exponential piece, so divide both sides by 5. Now take the natural log of both sides, and you don't even have to do this. I mean, this is fine because it is a terminating decimal, so this is a precise number. It's not a rounding. But if this was like 17/3, you wouldn't want to truncate it. You could just leave it as natural log of 17/3. And then go from there. Once you have a natural log, right, when you have natural log of something to a power, we know the rule is the power comes down in front, and that's what happens here. The power comes down in front, you're left with natural log of 2 and then natural log of, the 17/5 over here. We're trying to solve for x, so we want to isolate x so we can divide both sides by this natural log because it's just a number, right? So here's our two natural logs, and then we can add the 3 over here to solve for x, and you could type all this into your calculator and get this nice approximation and round to whatever decimal of preciseness you need. Another example, here's another thing with two different bases, right? 5 to some stuff equals 3 to some stuff. Same technique. In order to rescue our variables from those powers, right, from being stuck up there as a power, we just take a log of both sides. And we could take a log of any base, right? We could take log base 2 or log base 3 or log base 10 or anything. But the problem is we're eventually going to have to evaluate these logs of numbers, and we can only do natural logs and logs in our calculator. So you might as well just get in the habit of using natural log. It's kind of the more common of the two. So just take a natural log of both sides. Powers flop down in front. Now we have to distribute because we need to get this x out of the parentheses, right? It's trapped inside the parentheses. Now I know in the previous example when we were at a step like this, we divided both sides by natural log of 5. But the only reason why we could do that is because this was the only x, right? We've got another x trapped over here. So we're going to have to distribute both. And now we have an x piece here and an x piece here. And then we're going to bring that one over so all of our x's are on one side and then the constants are on the other. Factor that x back out, right? So we can divide both sides by this, which is just a number, right? It might look scary, but it's just a number if you plug it into your calculator. And that's where it is when we divide. So plug all this in your calculator and there's your answer of almost 2.8. How about a similar example? 3 to the x minus 8 times 3 to the x equals 2. And this is 3 to the minus x, right? Well, just like when we're dealing with fractions and we want to get rid of fractions by multiplying through, 3 to the negative x is, really 1 over 3 to the x. 3 to the negative x equals 3 to the x times negative 1, right? And that's 3 to the x to the negative 1, which is just 1 over 3 to the x. And we don't want to deal with that, so we multiply through both sides of the equation by 3 to the x to cancel this out. So 3 to the x and 3 to the negative x are going to become 3 to the 0, which is just 1, right? That's just 1. So all of that was just so we could get rid of that fractional piece. Now we have this. Now you might want to think about, well, can't I just take natural logs now of everything? And you could, but there'd be a slight problem with that, because if you took natural logs of both sides, you can't take natural log of this piece and then this piece and this piece. You would have to do natural log of all of that, and then natural log of all this. And that's not going to do what you need it to do, as far as bringing this power down, right? We don't have a way of dealing with log of something minus something and splitting it up. We have a thing for dealing with log of this minus log of that, and then we can just make it log of its quotient. But that's not what we have here, right? We have to take log of the left side and log of the right side as one piece. So you're not taking log of each individual thing. Taking a log of something is not like multiplying by something. If we were multiplying both sides by 2, then of course we would multiply each piece by 2. But that's not what we're doing when we take a log. A log is a function, right? We're taking all of those things and we're pouring it into a function. That becomes the input of our function. So that entire chunk becomes the input of the log function. It's kind of like squaring both sides of an equation, right? If we were to square both sides of that equation, we wouldn't square 3 to the 2x and then also square negative 8. We would have to square it as a whole, as one piece, right? And then we would have to FOIL it out and do all that ugly stuff. So taking logs of both sides is not going to work here, because it's not going to enable us to rescue that 2x out of the power of 3. Instead, if we move this x piece over here, we hopefully recognize this as a quadratic in disguise, because this right here is just this thing squared, because 3 to the x squared is just 3 to the 2x, right? A power to a power, you multiply the powers. So that's what we're talking about down here, is recognizing that this is a y and this is a y squared. So with a simple substitution, we can now visualize how this is in fact a quadratic, and then we can factor it like we do with quadratics. We can solve it like we do for quadratics. Then we can bring the 3 to the x back in and set them equal to the answers we just got, realizing, however, that this one doesn't work, because 3 to the x can't be a negative number, because 3 to the x is always positive. So this is our only solution here. And that's the one that we continue on. Now that we have a simple thing like that, now we can finally take natural logs of both sides to solve for x. Move the natural log of 3 over, and we finally get that x is almost 1.3. Okay? Some more applied problems with these things. So really the same stuff we've been doing, only now we're going to throw it into a word problem. They give us some populations of 2 countries, United States and Pakistan, in 2010. They give us the approximated annual population growth rate for both, and then they ask some questions. Using this population model, not the E one, right? We're normally used to using E for population growth. They want us to use this one. Can we estimate what the populations are in 2020? Can we figure out what year that we'll have 350 million in the United States? And then can we figure out what year that the 2 countries will have the same? Part A, using this formula, right? Plug everything in that we know. They told us that in 2010 the population was 308 million. So there's our initial population. And then the growth rate they gave us, right, 9%, or sorry, 0.9%, so there's 0.009. In 10 years, in 2020, the population will be the initial amount, there's our R, and then T is 10 because this number 308 comes from 2010. So that means T sub 0 is 2010, right? This is T equals 0. So this becomes T equals 10. And we get a simple answer there. Do the same thing with Pakistan. We just used their initial population in 2010 and then their growth rate and get their answer. Pretty straightforward, pretty easy ones. Okay, what about solving for a particular time? They want us to figure out when will the population be 350. So that's the output, right? 308 was the initial amount. There's our growth rate. There's our T. All we got to do is solve for T. So we isolate it, divide by the 308. Take the natural log of both sides, because that brings the T down in front. Then divide both sides by the natural log of 1.009, and this is what T is. See, it's better to leave it like this the whole way through rather than to take what the natural log of this is, what the natural log of that is, and have two decimals and then divide by those decimals, because then you're just rounding on top of rounding on top of rounding. If you can do this algebraically, then type all of this into your calculator at the end, you're getting a much more accurate answer. Third one, figure out when the two populations will be the same. So here's the initial population for the United States, the initial population for Pakistan, right? The growth rate for us, growth rate for Pakistan, and then we're solving for at what time are these two things equal to each other. Very, very simple. Divide both sides by 185, then divide both sides by this. Basically, we're just putting the t's on one side and the non-t pieces on the other side. So we're still isolating our variable. It just feels a little weird. This piece here might seem like, what the heck happened? Well, if you have 1.021 to the t divided by 1.009 to the t, right? Two things both to the power of t, then you can combine them and say it's that whole product, sorry, the whole quotient to the t. So that's what happens there. That's how they got to that point. Now take the natural log of both sides, which is going to bring this t down in front, right, which is what we have here. Now divide both sides by this. Remember, it's just a number. So this is what t is. Plug all this into our calculator, and it's going to take about 43 years, or basically 2053. Okay, how about solving some logarithmic equations? Well, logarithmic equations can be in all sorts of different forms. You can have the simple, easy ones, like these, which are kind of like the simple, easy exponential functions we had. Then you can get ones that are a little bit more complicated and even a little bit more complicated, but it's still pretty easy. To solve the first one, it's pretty easy, right? All the bits and pieces are there. If we're solving for x, remember with a logarithmic equation, it's just saying this to this power equals that. So very simply, x is just going to be 2 to the 4th or 16. Something like this, if we're trying to solve for x, the same rules apply. Isolate our variable. So you move the 4 over, divide by the 3. Now you've got it in this form, and now you're back to this power equals that. So 2 to the negative 1 equals x, and 2 to the negative 1 is 1/2. Now you always have to check your answers with logs. It's just like when we take the x squared equals 4, and you take the square root of both sides, and you get x equals plus and minus 2. And sometimes, depending on the context of the question, maybe the negative 2 doesn't work, and so you end up just saying x equals 2. Same thing with logs, is because we know logs are only defined for positive numbers, right? Their domain is above 0, right, greater than 0. We have to check things. So we plug in the 1/2, do all the work, 1 equals 1, it's good to go. A slightly more complicated, ugly looking one, but it's still pretty simple if you just follow the steps. Your goal is to get 1 log equals 1 number, or 1 log equals 1 log, those types of things. You're trying to simplify things. So instead of having 4 logs, try and get it down to 2 or 1, right? 1 on each side or 1 altogether. On the left-hand side, you'll notice, well, they're both base 4, so I have a log of something plus something, and the rule is that becomes log of their product. On the right-hand side, they're also both base 4, so that sum becomes a product. And now that we have log base 4 of some stuff equals log base 4 of some stuff, well, hey, that's just like before when our bases of our exponentials were the same, right? When we had 3 to the x equals 3 to the 5, we knew that x had to equal 5. Same thing here. So now we know the bits and pieces have to be equal. The logs just pretty much go away. It's kind of like taking both sides and just making them the power of 4. And we know that they cancel out. Now we're left with this, and if we were left with this and we had to solve for x, we go back to our normal set of tricks and techniques and go, all right, well, I got to multiply it all out, see what I have, combine some stuff. Now I'm left with a quadratic, factor my quadratic, get my two answers, 2 and 3, and now check them both. Plug 2 in, everything checks out. Plug 3 in, everything checks out. So they're both part of our solution. Another one, similar example. So we have a log base 2 of some stuff, another log base of 2 of some stuff. Remember, equals just a number, and when we have the same base, we can combine them as a product. Now we have log base 2 of some stuff equals 1. And now that we have one log and one number, we know that it's this base to this power equals that stuff. So 2 to the 1 equals that stuff, or 2 equals this stuff. We squared it all out to get this nice thing. We moved the 2 over because we recognize this is a quadratic and said, got to set it equal to 0 because that's the only way I can solve a quadratic. Factor it out, get my two solutions, and check them. Put the 2 in, and look what happens. 2 minus 3, 2 minus 4, and we get a log of a -1 and a log of -2, and that's impossible. Logs are not defined for negative numbers. So 2 is out. Can't be a solution. Check 5. 5 ends up working okay, and so we end up having that our solution set is just 5. Another one, similar. It's a sum, so it becomes a product. Again, we know that it's this raised to that, right, equals this. So this stuff is 2 to the 1, or 2. We recognize this is going to be a quadratic, so we multiply it out, move the 2 over. They just skipped a step, right, because this would have been 12, and then you move the 10 over, that's why you get 10. Now try to refactor it so that we can solve. Get our two solutions here, -2 and -5. Check each of them. Plugging in -2 seems to work out okay. Plugging in -5, however, leads again to that problem of negatives inside the logs, so -2 is our only solution. Okay, how about the logistic growth model? So just like the exponential growth model, we can have a logistic growth model, something that grows with a log function rather than an exponential growth. You might be going, yeah, but isn't this exponential? Yes, it's exponential, but it's down in a fraction, and because it's in a fraction, it's going to grow more at a logarithmic rate. In any case, they want us to, what are they asking for? Calculate the average growth rate k for the population growth, and then they also want us to figure out when it's going to hit certain things. So we plug in what we know. We know that in 1987, we're going to call that time 0. The population was 5, and the m, right, the total sustainable rate thing was 35. Plug all that in, 5, 35, 0. The 0 makes the e go away. We're left with just 1 over a. To solve for 1 over a, of course, we multiply both sides by it to get rid of this fraction. So 5 times that equals 35. Divide both sides by 5 gives us this. Subtract the 1 gives us a equals 6. And so we've now solved for a. We can put that back into our equation. Same equation, we just now know what a is. Now that we know what a is, we can solve for k with our second piece of information, which was 16 years later, right? 2003 is 16 years past our starting point. So the starting point that we used, right, which was 87. So that's why this is t equals 16. The population was 6, so we put in 6 for the population. We still have 35 for m. We got the 6 from a that we solved before, and now we just put in 16 for t. Remember, this was negative k times t, so when we put in 16 it was negative k times 16, and all we did was just wrote it in this direction because it's usually more common to write the constants first and then the variable after it. Okay, now we got to solve for this k. So the first thing we want to do is get it out of this fraction. Multiply both sides of the equation by this whole bottom, right, by the whole denominator piece. And so that's why it's 6 times all that equals 35. Now again, we want to solve for k, so we need to isolate it, so we need to get it out of our parentheses. So we distribute the 6. Then we move the 6 over, which gives us 29. Then we divide by 36. So now we're to this point, right? Now the last step is take the natural log of both sides, and when you take the natural log, right, when you take natural log of this and natural log of this, natural log of e to the stuff just gives you the stuff, natural log of this is just a number, which we can now divide both sides by 16, which is the same thing as multiplying by 1 over 16, but you could have just had natural log of all this stuff, right, 29 over 36 divided by negative 16. Same thing. That's your k. Plug it all in. That's what you get. So the growth rate is approximately 1.35%. Okay? Last but not least, we can use some logarithmic and exponential properties to solve inequalities. Really no different than when we're dealing with equalities. The only thing we have to worry about is the one thing we always have to worry about when we're dealing with inequalities is if we multiply or divide both sides by a negative number, we have to remember to flip the direction of the sign. So we would still treat this like we would any other exponential function. If we're trying to solve for x, the first thing we want to do is isolate it. So we move the 3 over, which gives us 15. Then we divide by 5, which gives us 3, right? So that's how they got to 0.7x equals 3. Now, to solve for x, we take the natural log of both sides, so that'll take the x down, gets us to this point. Now to solve for x, we have to divide both sides by natural log of 0.7, but here's where it gets tricky because natural log of 0.7 is less than 0. If you didn't know that, that's okay. It's just whenever you're taking a natural log of something less than 1, between 0 and 1, you're going to get a negative number, and greater than 1, you're going to get a positive number. If you don't have that memorized, just plug it in your calculator and get it, figure out what it is. And you go, oh, look, it's a negative number. So when I divide by it, the sign flips. Now, plug everything into your calculator this way so you don't have any rounding issues, and there's your answer. X has to be bigger than negative 3.08. This one. Well, whenever we're taking log of some stuff, we always have to remember that the stuff, right, the big difference between that one and this one is we had e to some stuff, right? Or not e, but we had an exponential, so x was the power. And when we have a power, x can be anything, right? Exponential functions, the domain is all, so we don't have to worry about it. But this, logarithmic functions, the domain is everything greater than 0. So the first thing we have to do is figure out what's the domain of our x, right? What values can we plug in for x? So you take 2x minus 5 and go, well, that stuff, right, this entire piece here always has to be greater than 0. So you set it greater than 0 and solve. And you get that x has to be bigger than 5/2. Okay, part 1, done. Part 2 is solve the thing. If we want to solve for x, we got to get it out of this log. So to undo a log, we have to do an exponential both sides, and we do an exponential based on the base of the log, and log with nothing written in there is base 10. So you do 10 to the left-hand side, right? 10 raised to this stuff is 10 raised to this stuff. So 10 to this is 10 to the 1. These cancel, and you just get 2x minus 5 equals 10. And from here, it's just a simple inequality, right? Add 5, there's your 15, divide by 2. So x has to be less than or equal to 15/2, but we also know that x has to be greater than 5/2 as part of the domain. So the total answer is combining those two, and we get this. Okay? And that's the last example of working with log and exponential stuff to solve inequalities and equalities. Pretty basic stuff. Remember, we're still using all the same rules that we use for solving equations or inequalities. We're only now using a couple extra tools to deal with the certain part of the equation or the inequality that involves either the log or the exponential. So we're not learning a whole new set of rules. We're just learning one new kind of variation on a theme. And if you think about it that way, it's not so daunting.